Hey everyone, and welcome to a new video. It's Federico here, and in this video we're attempting at something pretty complex, which is generating this grass using the power of the GPU. So this whole thing is generated in a shader, GGL shader, especially in the geometry shader. So we are rendering the vertices of this grass directly from within the GPU using geometry shaders. And this is something that I was inspired to do because I was looking for how to render grass in computer graphics. And then I found a tutorial on YouTube from Simon Dev, which it's not really a tutorial, just he shows how he does it. And then I tried my take on that. So I don't know if I got everything correctly. A lot of stuff could be done differently. A lot of stuff could be done much better, I guess. This is just like my attempt to create grass in a shader in Max. So I hope you like the video. It's a pretty long one and could be a bit scary. So if you just want to get the patcher, you can get it from my Patreon. Otherwise, if you are brave of heart, then go on and check out the video. So without any further ado, let's start reaching into the rabbit hole. Okay, so we are not starting completely from scratch. As you can see, I've got here JIT World, which is on 60 frames per second. And then we got a JIT anim drive, a JIT GL camera to move around in the scene. The world is called grass world, so everything will be rendering to grass world, every GL object. Then we got the GGL environment in which I loaded this beautiful skybox of like autumn forest and the skybox to draw it. And then I got the floor, which is basically just a cube scaled by 10 on the x-axis, 0.2 on the y, and 10 on the z. Attached there is a GGL PBR, so this reflects the light of the environment as well. Now I would like to make this a bit more interesting, so I would like to load a diffuse texture here and maybe also a normal texture, and I'm going to use for that couple of images which I downloaded from a website called ambientcg.com. I will put a link in the description, it's all for free. So that's the diffuse texture and that's the normal texture, and let's see how this looks like. And it looks like this. Actually, the texture is not a square, so I need to repeat the texture on one of the axes, something like that. Looks good. And anyway, yeah, this is just for fun. It's not really needed, just to give like a ground where our grass can grow. Cool. And now let's create the object which will be used to draw the grass, which is GGL mesh. So let's give it the rendering context, color white, and I don't know, draw mode. We want to draw points. So draw mode points, and I think this is it. And let's create a JIT gen here, connect it to the first inlet. Let's create here a JIT noise, 3 planes, float 32. Let's start with 10 by 10. So this will give us 10 by 10 grass blades. Let's bang it. It's actually load bang it. So when we start the patch, this will automatically send the matrix to GGL mesh. And the second output, we just want to send out texture coordinates, so we can use the normalized coordinates of the cells of the matrix. And here we can use like random values that we get here from JIT noise. So we can use like sweet x and y and use those as the y and x and z values for the position of those vertices. So let's go back here, let's bang that, and let's actually connect this to the second inlet here, which is the texture coordinates, which we will use then in the shader later. And we don't see anything. I think the points are first too small, so let's set the point size to 10, and then we need to bring them a bit up because otherwise they will be inside this cube. These floors. So let's set position to 0, 0. How big is our cube? 0.2, so let's make it like 0.25, 0. And there they are. As you can see, there they are. Let's scale their position so they will cover the whole plane here. So let's multiply that by 10. Maybe we want to multiply before switching, although it doesn't make any difference because the y will be multiplied by 0, but just in case, let's put it there. They are only on the positive axis, so we actually need to rescale between Let's actually use a scale object and say scale 0 to 1 between -10 and 10. That should do it. Right. So we got 100 points scattered around this plane. Great. Let's now transform those points into grass blades. And to do that, we are going to use shaders. We are going to use the geometry shader. So let's create a GL shader object that draws to grass world. And let's give it a name and call it like grass shader. And the file, we're going to call it grass shader tut.jxs. Now this file doesn't exist. So what I'm going to do is to double click here, get the default shader code, right? Go inside Visual Studio Code, create a new text file, and just copy that inside there. And then I'm going to use the GLSL syntax highlighting, and then I'm going to save it into the folder where I have saved the patcher, this patcher here for the tutorial, and we said we call it grass shader tut.jxs, so the name must be the same that we set here in the file attribute. Cool. I'm not going to go into super details about shaders in general because these I covered in a lot of other videos, so you can check those. I will put links in the descriptions if you don't know exactly what's going on with shaders in Max. So we'll go a bit faster. Let's change the shader description to like, let's call it grass shader, and the name as well, like grass means shader. And cool, so let's see what we need to change here. So first of all, here is our vertex program. It takes the bunch of inputs from Max, so like the position and the color. These are vertex attributes that come in from GGL mesh, and then there is the model view projection matrix, which transforms the position from local space into screen space. And this is what we do. We assign the position transform to the GL position built-in variable that then will pass it to the geometry program. Now, in the geometry program, we don't need, after the closing line of the vertex shader, that is the opening line of the geometry program, and we don't need this stuff here. We can delete everything and just leave the name of the program, which is GP, and the type, which is geometry. Cool, because it's just a repetition of what is written already here, which is layout. This is the input type that the geometry program expects to get in, which is lines adjacency. We actually want to get points as input. Now, a geometry program in a shader doesn't get vertices as input, it gets primitives. So the primitives possible types are like lines, triangles, and points. And since we want to transform each vertex into a blade, we want to input points and output a triangle strip. A triangle strip is just a bunch of vertices that, when output from a geometry program, each 3 vertices will create a triangle. Sorry, I made a super bad line. There we go. So if we keep adding vertices, every 3 vertices we will get a new triangle, which will then create a 3-dimensional shape. In our case, they will create our grass blade. So the max vertices that we want is 15. This is kind of a nice number of vertices to create a grass blade if we want to bend it. So it will give us enough resolution. And then these lines here, as you can see, this is the GLin, GL position. This GLin is like a built-in variable that gives us what's coming in from the vertex program. It's an array because, as we said, the geometry program gets primitives as inputs, not single vertices. But our primitive is a point, so it is indeed a single vertex, so we don't need these lines here. Anyway, we're going to change all of these. And then we got the fragment program, which what it does is sets the appearance of the pixel that compose our 3D shapes in the screen. So let's start by creating our grass blades inside the geometry program. So what we're going to do is indeed to create a for loop, and in each for loop we will create a vertex of the grass blade. So we will output the first vertex and the second at the same height, and then we'll output the vertex 3 and 4 and 5 and 6 and so on until we arrive to 14, and then the 15th vertex will just be the top of our grass blades, which we will put outside of our for loop to finish the grass blade with a nice pointy point. First, what we need to do is to get the model view projection matrix not in the vertex program, but in the geometry program. Because in the geometry program, we want to work in local space. So we don't want to work in screen space. So we will just pass the GL position, just the local position, which is basically the values that we get here from JIT_gen in the matrix. And then we are going to cut the uniform model view projection matrix here and put it inside our, let's actually put it a couple of lines below after the layout. And what we need to do is to go here when we bind the params and set geometry program instead of vertex program. All right. And then what we need to do here is to multiply our local grass vertex position by the model view projection matrix. So let's get our local grass position. And as we say, we wanted to create a for loop. So for int I equals 0, I is less than 14, I plus plus. We can actually even define the number of max vertices with a define preprocessor statement, I think it's called. So we can use it here and we can use it here, but -1, right? So inside the for loop, what we want to do is to create a vector. It's going to be the grass vertex. And let's set it to 0 first. So 3 elements set to 0. Then we want to set the width of this grass vertex. Now the width, let's set it to a default value of 0.1, just to start. And then we want to also get the height of the grass blade. So let's first create a variable and call it normalize height. This will be the height going from 0 to 1 for each couple of vertices. So in our blade here, the height will be 0 here, then I don't know, like 0.1 here and 0.2 here. So 2 vertices will have the same height value. This will be 0, this will be 0.1 for vertices 3 and 4, 0.2 for 5 and 6, and so on. So let's go here and say normalized height is equal to I divided by 2, and this is an integer, so it will only return integer values. So the first 2 vertices will be 0. So when I is equal to 0, this will return 0. When I is equal to 1, this will return 0. When I is equal to 2, this will return 1. And when I is equal to 3, this will return 1 as well, and so on and so forth. Then what we want to do is to divide this by 6. Because I is going to go from 0 to 13, because it must be 1 less than this value. But we are dividing by 2, so it's going to arrive here up to 6.5. But remember, this is an integer division, so it's going to arrive max to 6. So this will give us a value that goes between 0 and 1. And every 2 grass vertices in this for loop will have the same height value. So let's do like this and say grass vertex is equal to vec3 width, and then normalized height, and then 0 for the z-axis. We don't care about the z-axis. This is only the local vertex of the blade, so we just care about the x and the y. Actually, the first vertex should be like minus width, right? Because we want to place this vertex on the left of our grass blade. So let's say that this is our central point of the grass blade. This is our width. So minus 0.1 is going to be here on the left. Then we want to create the next vertex also at width. And this will be at 0.1. And then we want to go up in the height, create a new vertex here at minus 0.1 width, and so on. Create the other one at 0.1, but with a different height. So we build our grass blade in this way. So what we want to do basically is to check if I is an odd value or an even value. And there is a trick to do that. It works like this. If I, bitwise AND operator, 0 per 1. So this will take the last bit of I. So this is either 0 or 1, right? Because in binary numbers, we only have 0 and 1s. So if this is even, this is going to be equal to 0. And if this is odd, this is going to be equal to 1. So actually, you know what we can do to be really clever? We can say that width is equal to the bitwise AND operator. And then we can subtract 0.5 from that. So when this is 0, width will be minus 0.5. When this is 1, this will be 0.5, right? So we get that our width now goes between minus 0.5 and 0.5. According if the value here is, the value of I is even or odd. And so, cool, this should work. Let's now emit this vertex. So inside our for loop, we want to get this and pass it inside here. We actually don't really want to pass the color to the fragment program, so we can actually remove it here from our jit out structure. And we can also remove it here from here. We can just assign manually the color white for the moment to the grass blades, because we will anyway set our color manually. We will not pass it from the geometry program. And then what we want to assign to the GL position is not the input position from the vertex program, but just we will start with the grass vertex position. So let's see what we get. And we don't get anything because... oh, because I put a comma here, so this shader is not being seen by Max. So let me reveal it in Finder and rename it. So I rename it and reloaded it inside Visual Studio Code. Now, if I save it, we should see something happening here. And when I recreated the shader, we see that I get an error. There is an equal that is not really, should not be there. And I suppose that is this max vertices here, the preprocessor statement, which is wrong. And there is another problem with the parentheses apparently. So let's see. Oh, this I think, by the way, this is vector 4. So I guess we need to set this grass vertex, which is a vector 3. We need to add like a fourth value here, and we will set it to 1. And we will see later why we are setting the last value to 1. But we still get these errors. So let's see what's going on. Could this be that this is because this structure is empty? Let me check float test. And we will set it also here equal test, just to see if this was the problem. And it looks like that was the problem. And we have now our grass blade that it covers the whole screen. And that's because this is in local position, right? It's not being transformed by the model view projection matrix to transform the coordinates into screen space. So that's why we see this big white rectangle. So what we want to do is to transform here, multiply the model view projection matrix by the grass vertex. And there we go. There it is, our grass vertex placed in the world. And we are using a 1 here because if we will not use any 1, you will not see any difference here, or actually you will. This one is used to multiply the translation component of the model view projection matrix by the grass vertex. And it's also something to do with perspective division. So in this case, we need to use a 1 here to have the multiplication be done correctly. Okay, so this grass blade, it's a bit too wide because it goes between minus 0.5 and 0.5. So what we can do is to multiply our width by something like 0.1. So it will go between negative 0.1 and positive 0.1. And cool, we got our first grass blade. We just need to add the last vertex, the 15 vertex, right? So in order to add the last vertex on top of the grass blade, let's copy that portion of the code. And let's pass it before the end primitive. End primitive, by the way, will basically output the primitive from the geometry program. So with the emit vertex, we are emitting the vertices of the primitive, and then at the end, we output the whole finished primitive, which in our case is this triangle strip. So what we want to do here in this 15 vertex is probably to set the height of the grass vertex a bit higher, so it will go outside of the rectangle here. And if you're hearing some cute noises, this is my baby, which is sitting right behind me. Cutest baby in the world, of course. So let's do something like grass vertex.y plus equals 0.05. I don't know if this will be how we do this ultimately, but This should be fine for our purpose. The only problem is that gross vertex is defined inside this for loop, so in order to use it outside the for loop, we need to define it outside the for loop. And if you're wondering how I did that, Visual Studio, I'm just pressing Option and arrow up and down to move a line above or below. Okay, so this should now work, and as you can see, we get the point. The problem is that it's not centered. So what we also want to do is to set gross vertex.x to 0. And there we go. We have our pointy blade. Now, it doesn't really look like a gross blade, and I think that's because the width is constant for the whole height of the blade. So what we want to do is probably to multiply the width. Let's put it out after the normalized 8. We want to multiply the width by normalized 8, and this should give us reverse, actually. So 1 minus normalized 8. And this gives us a triangle, right? Which is not exactly what we want. We want we want the blade to like start wide and then restrict close to the tip, but not really like all the way like a triangle. So what we can do is to use like a smooth step, which we will then reverse. So let's do like this. When the height is smaller than 0.2, it's gonna give us a 0, and when the height is bigger than, I don't know, 0.8, it's gonna give us a 1. So we want to reverse that, because this will look like this, right? But we want to reverse it, so it's the other way around. And this looks more as what I wanted. I think we just need to make this value bigger. Let's see, maybe this value actually bigger. So it starts, all right, this looks more like it. It's maybe not 0.5 or something. Yeah, this looks good. This looks good. Let's maybe reduce the width a bit. Right, this could be our gross blade. Let's maybe make it taller. So let's here create a new variable called the height, which is equal to normalized height by, I don't know, like 1.3 or something. In this way, the blade will be taller. I am liking it. I think I want to have it a bit fatter going up. So, right, something like that. I think it could be all right. Maybe 1.2. Yes, 1.2. I think it's going to be okay. So, let's go now on to the fragment shader. And let's start to color these blades. So we could create a bunch of colors like dark green, for example. And I'm just going to improvise here and create a color that I think will look like dark green. I don't know, I'm just putting a bunch of semi-random. I mean, it's not really random, it's just what I think could be a dark green, but I have no visual reference for that. Okay, this looks pretty nice, actually. Now I want to have a lighter green. So I want to have like a yellowish lighter green. So we got to have a lot more red, a lot more green, maybe a bit more blue. And let's see how this looks like. Yeah, I want to have it a bit more yellowish. So I'm going to increase the amount of red here. Yeah, this looks more like it. So what we want to do now is to interpolate between dark green and light green on the length of the blades, so that it will like smoothly go from dark green to light green. In order to do that, I think we need to pass from the geometry program the normalized height to the fragment shader. So let's write here, instead of calling test, let's call it height here. And the height will go from 0 to 1, so we're going to use the normalized height. So we need to pass for each vertex these values. So let's go after normalized 8, and this structure doesn't have a name. So we could just, in case this structure doesn't have a name, we could write like height equal to normalized height, right? but this will conflict with the height that we are declaring here. So in order to avoid this sort of confusion, I like to give a name to the output structure as well, like it is done in the vertex program, where the structure is called jit out, that we call jit out as well. So this will be jit out dot height is equal to normalized height. And now inside the fragment shader, we can use these values. So we can say that let's create a new variable. Let's call it like frag color. And this is going to be a mix between dark green and light green using jit in.height value from our structure. And then we need to, of course, use this value here. So cool. That looks like slightly like a grass blade. What I like to do now before we go on is to apply gamma correction to these colors. And you know what? In all my years of making tutorials about graphics in computer graphics in Max, I never really used gamma correction in my visuals. But actually, it is like this, that the colors that we are using here are in linear space. And then when the monitor displays them, it converts the color to sRGB space, which basically applies its own non-linear transformation to the colors. So in order for us to visualize those colors correctly, as we meant them to be, we should make the opposite conversion that the monitor does, which is to say we should apply the gamma correction. And this looks like this. We basically need to say frag color.rgb is equal to the power of grass color RGB, frag color RGB, power of 1 divided by 2.2. So that's it. And that's how the gamma corrected color looks like. It's usually a bit brighter. And lo and behold, the PBR object already has gamma correction included. So we can also deactivate, and that's how the colors will look like if we just go from linear space to sRGB screen color space. And if we apply the gamma correction, it will look like much better. So we should always apply the gamma correction. I just never did it. Nobody dies, nobody gets hurt if this is not done. It's perfectly fine, just so that you know that this is a thing. And if possible, we should always apply gamma correction. There is even a pass in Max, which lets you use gamma correction. I don't remember exactly how it's called. Let's go in the reference and we will see it here. It's called gamma. Right, doesn't only do gamma correction, does a bunch of stuff, so I encourage you to check these out. Great, so gamma correction. Now, I would like that the green color, it's not like linearly interpolated on the blade. I would like that it goes like greener, a dark green until almost the top, and then goes into this light green at the end. So instead of using jit in height as it is, we are going to make a new variable. We are going to call blade color interpolation amount, or just blade color interp, and this is going to be the smooth step of 0.61 of jit in dot height. So we're going to use this value to mix between the two. So let's copy that and replace jit in dot height with that, and so we will have that the green color is almost to the tip, and then it becomes like light green. If we want to have more light green, we could reduce this to 0.5, or if we want more dark green, we could augment this to 0.7. Something like that. I think 0.6 was fine. Cool. So that's our first blade. Now, let's create a bunch of those blades. And in order to do that, we already got our random position coming in from JIT_gen to GGL mesh. So we just need to sum our local grass vertex position with the position that comes in from the vertex shader, which is in GL position. So let's create a new variable here and call it like blade offset or so, blade position actually. And this is going to be simply the GL in 0.gl position, something like that. I think this is correct. No. Of course, this is a vector 4, so we should convert it to vector 3 like this. Okay, so that's it. So what we want to do is to simply sum this blade position to the grass vertex. So we can do like this, grass vertex plus equal blade position. And we need to do the same here. And we should have now a bunch of grass blades. Oh, it works. It's only that the last vertex is somehow way wrong. And let's see why is that. All right, because we already sum it to blade position. So we should not sum it again here to blade position. I guess we just don't need to sum it there. Right, that's it. We got a bunch of grass blades, and if we would want to have more, we just can set a dimension here, 200, 200, bang this matrix, and then we'll have a bunch more grass blades. Cool. Now the problem with that is that they are all oriented in the same direction, which then doesn't look very realistic, right? They all are turned to the same direction. So we want to, the next step, we are going to turn those grass blades in random directions. So in order to do that, we need to get a rotation matrix to rotate those vectors, the grass vertex local position, into the y-axis. So I'm just going to copy paste this matrix, this function that returns a matrix to rotate around the y-axis. If you want to know how this works, you can check out the Wikipedia page around the rotation in 3 dimensions. So what we want to do is to rotate the grass vertex. Before we sum it to the blade position, we want to rotate it by some angle. So rotate 3D Y, and let's just pick a random angle in, this is going to be in radians, right? So I don't know, just 0.707, which should be like 45 degrees, something like that. And then we multiply this by grass vertex. And I guess this is it. We don't really need to do it on the other axis. No, we actually need to rotate that as well, which is a bit annoying. Okay, so I don't think this approach that I used of declaring the grass vertex outside here is actually what we want to go with. So let's put it back in the for loop, and let's actually expose the height here. So we don't need to redeclare it here. And here we're going to say vec3 grass vertex top is equal to vec3 0 for the y, 0 for the x, and then height plus 0.05, whatever it was, and then 0 for the z. And then we want to rotate it. Then we copy that. I don't know if this is the best way to do that because we are duplicating some code, so probably there is a better way to do that, but whatever, it's not gonna hurt anybody again. So let's sum them to the blade position, and let's use that as the final vertex here. And there we go. So let's see. They should be all rotated around the same angle. Let's try another angle. So they should rotate these. Yeah, they're rotating. Cool. So let's now use some noise to rotate the blades into all different angles. So we could pass some noise from, even from JIT here. We could use a vertex attribute to pass some noise from max. What I'm going to do though is to use some procedural noise to create the noise directly inside the shader. We are going to copy some code from GLBFG, which is the object in Max that is used to create like noise textures, right? As you can see, it has a bunch of functions, all giving us different type of noise. This is exactly what we want. So what I'm going to do is to go here, say get GL3 shader from GLBFG, and what's happening is that this gives us the code that is inside GLBFG to create the texture. And then I'm going to go in Visual Studio Code, I'm going to create a new text file, copy that, and I want to get rid of everything that is not the functions to create the noise. So I'm going to delete the end here. And I'm going to delete all the shader stuff, all the uniforms as well. We don't need anything of that. So let's take one of these noise. For example, we have Perlin noise, we have simplex noise. And I think we want to go with simplex noise, which is perfect for our purpose. Now, simplex noise, it needs to work in this permute function and this mod 289. So let's just copy all this part until the simplex noise implementation is over. So let's copy that. Let's go in our grass shader 2 tier, and we could include this file as it is, but I found a bug for which when you include a external file in a shader, it will not recognize the functions unless you delete the shader, the GGL shader object. So instead of including an external file, I'm just going to copy all this code inside of our geometry program. And in order to distinguish between the noise code and our geometry program, I just put it on before max vertices here. I will just separate with these beautiful slashes. Cool. So now we can use simplex noise. So let's go inside here. Let's create a noise value. So here, let's call it noise value, and let's call the sNoise function. The sNoise function returns a float, and it wants a vector tree as input. So what we're going to use is a vector tree made of the blade position. So this is the seed of the noise, right? We're going to use x and z because y is 0, and then we're going to use 0 here for the z, something like that. So let's save, it's all good. So now we can use this noise val to rotate the grass vertices. Actually, this noise val goes between -1 and 1, I believe. So we can say noise val is equal to noise val plus 1. So I want to remap it between 0 and 1. So if we sum 1 to it, now it goes between 0 and 2, and then we can multiply it by 0.5. So now it goes from 0 to 1. Cool. Let's create a new variable here and call it random y rotation angle. And this is going to be the noise val times 2 pi. So let me actually get 2 pi as a number. Actually, let's go here and define it. So define pi as this number here. So 2 pi is simply going to be 2 times pi. And I'm using 2 pi because I wanted the grass can rotate like 360 degree. That's why I'm multiplying this by 2 pi. So let's then replace this hard-coded value with that. And we should now have that every blade is rotated into at a different angle, which is correct. Let's make the width bigger so we can see it better how they are rotated. Yeah, you can see that every one of these blades is rotated at a different angle, which is great. That's what we wanted. Cool. Maybe let's make them slightly thicker. Yeah, something like that. We could also assign to each of them a different thickness. Maybe we're going to do this later, maybe not. What we're going to do now is that we are going to bend this grass blade. So each blade will have a different, lean in a different way, as kind of real grass does. So what we're going to do is we need another rotation matrix. And this time is going to be a rotation around the x-axis. So I'm just copying again the matrix relative to that. And as you can see, the rotation around the y-axis leaves the y-axis untouched, and the rotation around the x-axis leaves the x-axis untouched. Let's get a new float here. And this is going to be the random lean angle. And this is going to be noise val, not multiplied by 2 pi. I don't know, I'm just going to multiply it by something like 1.5, because we don't want them to rotate completely like all the way, like curl on themselves, right? And I also want that they start to rotate the more as the blade gets tall. So I want just basically the tip to rotate. I don't want the whole blade to rotate, right? Because otherwise it would be a bit strange. Like grass doesn't rotate from the start, it just starts to curl from a bit above. So what I'm going to do is to create another rotation matrix here. And you know what? We could actually have we could combine those rotation matrices into a single rotation matrix. So let's create a mat3 here and call it like grass or blade rotation matrix. And this is going to be equal to the rotate 3D x by the random y rotation angle multiplied by the rotate 3D x. Sorry, before was y, now it's x. That rotates around the random lean angle. That's how matrices work. We can combine them together, and the final matrix will basically apply the same, the rotation of the two matrices combined. So that's pretty cool. So I just need to rotate both the vertex here and the vertex of the last vertex by that matrix. I'm gonna save, and whoa, right. So they are rotating, but as said, they are rotating from the base, right? They are rotating from all the way. So it's not like rotating more as the blade goes up. So in order to do that, this random lean angle should be also modified by the height. So I guess we should actually define this matrix inside the for loop. But then it will not be available for the final vertex. Okay, let's do one thing at a time. Let's first like define this matrix in the for loop, and the random lean angle should be, so let's go like here and say random lean angle must be multiplied by the normalized height. So what we can do is to declare this matrix outside the for loop, and then this is going to be initialized in the for loop, so that should work. And indeed it doesn't work. So user one declare identify, right, because I just assigned to 0, which actually we don't want. So we don't want to assign it to anything, I guess. And of course this doesn't work, and this because the random lean angle gets multiplied every time it goes in the for loop. So at the end, I guess it becomes it just becomes a value too small, because it gets multiplied always by a value smaller than 1. So what we should do is to create a new variable here and call it lean angle, and this is equal to random lean angle multiplied by normalized height, and then we use that as our rotation angle, and there we go. We get that the grass blades are all rotated on these angles. So this starts to look a bit more like grass. The only thing is that I would like that the rotation starts a bit more up. So we're going to use a smooth step, and the angle is going to be 0 when the normalized height is under a certain level. So let's do like this. Lean angle multiplied equal by smooth step. So below 0.6 is going to be 0, and then 1 of normalized height, and this should give us the... Okay, this is a bit too extreme, as you can see, so maybe we should reduce the value here, the random lean angle, to something like 0.7. Yes, let's start the rotation a bit earlier, so like 0.4 maybe. And this looks nicer. This is starting to look okay to me. Let's reduce a bit more the amount here. Yes, something like that. If we up the number of grass to like 200 by 200, let's see what we get. Oh, and as you can see, we get kind of a clear definition of the pattern of the noise. Let me actually show you how the noise looks like. So we're going to paint the grass with the color of the noise, so you will see what we're actually working with. So let's create a new variable inside the output structure, and let's say jit out noise bar, it's equal to noise bar, and then let's go inside the fragment shader. Let's create another variable here, let's call it noise val, and we can use that as the color. So jit in.noise val. Let's see. Right. So you can see how the noise looks like. Let's zoom a bit this noise out and in and see which value we are going to which value is going to serve us better. So let's create a new float here and call it noise zoom. And let's say this is 0.3. So we just need to multiply that by the noise zoom. And let's see what we get. Right. You can see that we are kind of zooming out on the noise, which then makes the rotation all look the same in certain areas. And if we go back to the frog color here, you can see how the grass looks like this. It looks like orientated along this noise. So if we want to have like really random numbers, we should zoom this noise very much in. So we can go here and multiply this by 10, for example. And then it will look like each one of them has basically a different value because we zoomed in so much that each single blade will have a different value, basically. We can also zoom in 100 to be really sure, but that should be completely fine. So let's go now in the fragment shader and get back to the frag color. And there we go. Fine, that looks fine. Maybe let's augment slightly the rotation amount to 45. Yeah, you can play around with those values yourself. What I'm seeing is that the last vertex is not rotated correctly. You see this kind of point going up, which is incorrect. That's, I think, is because the blade rotation matrix is taking into account the lean angle with the height at maximum 1, but here the height is at 1 plus 0.05. So what we're gonna do, let's copy the blade rotation matrix line again, and this should be not lean angle but random lean angle. If we do that, it's going to look like this, and I guess we need to account for this little difference in height, 0.05. By the way, I moved the height as the sum of the height here. So maybe we just need to add a little amount to straight the last little angle. I guess that's it. I don't think this works for all the bodies on the random lean angle. Indeed, it doesn't. So that's actually not the correct solution to that. Okay, so the experimental solution that I found, I don't know if it's actually correct, but is to add to the random lean angle 1/15 of the random lean angle, since this is the 15 vertex. And I don't know, does this make sense? Or should we actually divide by 7.5? It looks like by dividing by 15 we get a good result, so I will leave it like that, and this works for like all the possible values of random lean angle. So this is okay with me. I hope it's okay with you too. Otherwise, if you find a better solution, please let me know. Let's create 200 by 200 of them, so 40,000. And what I would like to do is to give to each blade a different height, because not all blades are made equal, right? Some are taller than others. So what I'm going to do is to multiply the height by the noise value, our good old noise value. So let's multiply this by noise val and see what we get. Okay, cool. I guess the noise value never really arrives to 1, so let's multiply this by 2. Cool, so now some are going to be taller and some are going to be smaller, and as small as these little stumps here, which is maybe a bit too small. So what I want to do is to clamp basically the height. Actually, let's clamp noise val multiplied by 2 between 0.7 and 1. Actually, if we multiply it by 2, then it should be, the maximum should be 2. And the minimum should be 1.5 maybe, or just 1. Something like that. So some are taller, some are not so tall. And oh, the problem is that if we use the same value that we use for the rotation, this will be correlated. So we should maybe sample a different noise value here. So we can do like this. Let's call this noise value, let's call it noise value lean. So this is going to be noise val lean. I think this is it. If I save here, yeah, seems this was okay. And let's sample again the noise value. So let's create a new float. Let's call it noise val height. And we are simply going to copy that. But we are going to simply sum an offset to that. So back to just a random offset in order to don't have them correlated. So I'm just putting up a bunch of random numbers here. And save that, and then we're going to use that for the height. And we need also to rescale that from -1 to 1 to 0 to 1. So noise val height, do the same treatment as the other. And cool, now it's not anymore correlated, the height with the leaning. Let's maybe have a bit more, but not as many as 200 by 200, so maybe 50 by 50, right. And let's clamp the height a bit more, so between 1.4 and 2, something like that. Yeah, these I like. Cool. Then another thing I would like to do is to give a different color to each of those blades. So in order to do that, we could go here in the fragment shader, use our noise val, which is basically the noise val lean for the leaning. So the color will be related to the leaning, but maybe it doesn't matter. If we multiply this by noise val, let's see, some are going to be very dark and some are going to be more bright, which looks pretty cool actually. So I'm going to clamp these again between like 0.7 and 1. So it's not going to be super dark. Oh, 0.7 I meant. Maybe a bit darker, so maybe it's 0.4. Right, this looks pretty cool. It looks a bit more like grass. So in this tutorial we are not going to use lighting, okay, because that will be quite difficult to implement lighting with the grass, because we don't really have access to the normals. We should calculate the normals ourselves, and this is still something that I'm working on. No proper lighting on this, we will have just to kind of fake it, as I'm doing here. I want to put the rotation a bit more, starting from a bit earlier in the blades. So what we need to do for that is to lean angle, we just need to make it start earlier, right? Okay, so this looks good. We can also augment the random lean angle here if we want. Maybe 55. Okay, cool. So what I want to do, let's go back to like 100, 100. What I want to do is to try to simulate the shadow of the grass blades, so that it looks like that all these grass blades kind of cover the lights, and so the bottom of the grass blades looks a bit darker. So what we need to do is to simply, we could just, for example, just multiply the frag color, multiplied by the jitter.height, and this will give us like this effect, which is maybe a bit too dramatic. So what I want to do is to clamp again the jitter height by 0.2 and 1, between 0.2 and 1, so that, yeah, actually instead of clamping in this case, we could just use the maximum value between jitter.height and 0.2. This is going to be the same effect. Cool. Yeah, this looks nice. Let's see what it looks like if we go with 200 by 200. Yeah, It looks sort of like a grass field. I want to have the tip of the grass a bit more yellowish, so I'm going to go here and get these like all the way up to 1 and here 0.82. Yeah, this is a bit more yellowish, maybe even like 88 or something. This looks nice. What I want to do now is to apply some wind to this grass so that it looks like that it's been moved by the wind. And it's going to be pretty cool. So in order to do that, let's get another noise sample here. So let's call this noise wind. And again, as noise. And let's actually copy this line. So we can use a different offset here. And then what I want to do is to use a different noise zoom. So noise zoom is going to be equal now to like 2, for example. Let's see how the noise wind looks like. So let's assign it to the output here, to jit out noise val, so we can see how this looks like with the, by just using it as a color in the fragment shader. And this looks like this. So we need to reduce the noise zoom a bit to like 0.2. Right, I want to have something like that. And then we want to animate this noise. So in order to animate this noise, we need to pass like some time parameter to the shader, some ever increasing number. So let's go on the top here and add a new param name. This is going to be the time. Actually, let's call it U time. So we know that this is a uniform. It's going to be of type float. And it's not a state, right? Because it doesn't come from max. We are declaring it manually. So we have to say default and just give it a default value. Close this. Close this, how is it called? Close this field and then bind it. Param, U time, program. We're going to bind that to the geometry shader, so the GP. And then inside the geometry shader, we want to go after the noise declaration here when we declared the monoview projection matrix, and let's declare the U time float. Cool. And then we basically want to sum that to, actually we don't need the offset then in this case, if we sum it anyway to the U time. So after we multiply by the noise zoom, we sum it to U time. And then in our max patch, we need to say jit time. This will give us like the time since the object was created in seconds. And then we say prepend param U time. And we attach this to the GGL shaders. And our noise is now animated. Cool. I'm going to use this noise as gusts of wind. So in order to do that, we are going to rotate the blades around an axis created by the strength of the wind. So in order to do that, we need a new matrix to rotate around a certain axis. And again, I'm just going to copy it from the web and pass it inside my shader. And it looks like this, rotation 3D. I'm going to put a link in the description on where you can find something like that, so you don't have to look for minutes in the internet. Okay, so what we need to do now is to define an axis around which the grass will rotate. And by the way, let's go back to setting the noise to noise val lean. This was what we had in the beginning. And in the primary shader, let's go back the color to frag color. Not visualize the noise, right? So we need to create an axis around which the grass will rotate. And this axis is basically going to be a vector that goes in each direction of like a circle according to the angle at which the wind is blowing. And the angle, we're going to use the noise wind for that angle. So let's create a new variable here and call it like wind rotation angle, and this is like equal to noise wind multiplied by pi, for example. And then we need to create the wind rotation axis, and this is going to be a vector with the cosine of that angle. 0 and then the sine of that angle so that the grass can rotate according to the direction of the wind. And by the way, this is all stuff that I learned from the tutorials from Simon Dev, which I encourage you to check out. I will put a link in the description. So once we have this window rotation axis, we need to modify our blade rotation matrix. And the first thing we want to do is to rotate around the direction of the wind. So blade rota mat is, or actually let's include another matrix here before we do the rotation around the random Y angle. Let's use the rotation 3D wind rota axis. And we're going to rotate at an angle which is defined by the wind strength. So basically the noise wind here, which goes between -1 and 1. So let's see. Let's multiply this matrix by the others. Let's go here and copy that here as well. The only difference here is that the random lean angle is going to be, that. Let's delete this. So let's see what we achieved. Whoa, this looks wild. So the wind amount is a bit too much. Let's create a new variable and call it like wind strength. And this is going to be equal to noise wind multiplied by, I don't know, like 0.1 maybe. And then we can use this one instead of noise wind here. Okay, and let me zoom out a bit the noise zoom, so like 0.03 maybe. Oh no, this is a bit too few, 0.05. This looks nice. The time is going a bit too fast, the animation time, so I multiply the time by something like 0.4. And this looks nice. Let's get the wind strength a bit higher, like 0.6. Yes. This is starting to look more like it. We could also apply the wind, so in order that it doesn't blow directly from the base of the grass, but starting a bit higher. And to do that, we would basically create a new variable here, which is float wind strength by height or something, which is the wind strength multiplied by, for example, a smooth step between 0.5 and 1 of normalized height. And then we would use that as the wind strength. Maybe a bit lower, like 0.2. Maybe it doesn't matter, and the wind strength should just, and the wind should just blow the grass from the base. Maybe that's fine as well. Okay, cool. And I think this was it with the grass animation. So if we want to change how the wind looks like, we could like zoom a bit more in the wind. So we have like some more scattered, but actually I liked it like that. This looks good. This looks like flashy grass. What I want to do is to make the fake shadow a bit more important. So I'm going to go in the fragment shader, and I'm going to, instead of using max here, I'm going to use smooth step and say that between below 0.1 this should be 0, and then from 1 this should be 1, and then maybe we just can add a little offset to that. I don't know, didn't change much, right? So maybe this is not really that useful. Yeah, maybe something like that. Could create a parameter to adjust the wind strength and the wind zoom and all the cool stuff. Let's create another version in which there are 150 blades. This looks nice. So cool. I will stop it here. Otherwise I could go on forever tweaking this thing. And thanks a lot for following me into this madness. I hope you liked it. Again, check out the video from Simon Dev. This was really instructive. The patch is available on my Patreon, and if you join, you will support the channel and have access to all the patches that I made in the past. So thanks a lot if you decide to join and support. I hope I didn't scare you too much, and I hope I will see you in the next video. In the meantime, have fun, keep patching, and take care. Ciao.